as it turns out, for whatever reason, and what further simplification could we desire? Despite having taken trigonometry, I don't have a good idea about how you would prove this. Trying to solve this question, what exactly does it mean to what exactly does it mean to solve the following trigonometric equations on the interval theta equals negative 2 pi to 2 pi? I mean, that has an explicit answer, I would say. Well, it would depend on your teacher. It would depend on what practice you're depend on what practice you're supposed to be expressing yourself through. In this case, well, we could set up each of the critical values and work through them. This was the most obvious process, or what immediately came to mind, which is we factored in such a way as to figure out where does this initial condition hold? Where is it initially the case that this, for what values of x does this equation hold? Hold on. Right, so this is a sort of, it's like a funhouse mirror distortion of what has become a rote understanding. What is that verbiage supposed to mean? What is this equation telling me? Suppose I put in pi halves. Alright, so we have 6 times the cosine squared of pi divided by 2. Okay. Minus 3 is equal to 0. Okay. Now I'm going to calculate this. We're going to get 6 times cosine of pi halves is 0, so this will be 6 times 0 squared minus 3 is equal to 0, which turns into saying negative 3 is equal to 0. Which tells me that this statement does not hold. Not 6 times the cosine squared of pi divided by 2 minus 3 is equal to 0. This equality holds at 4 points. I say the funhouse mirror distortion of this idea, which is that I wanted to plug this function into my graphing calculator to clarify my confusion. You can't plug this into a graphing calculator. You could plug this, you can, okay, so yeah, if we want to follow up on that idea, instead had 6 times the cosine squared of x minus 3 is equal to f of x. Okay, instead of 0. Then I am going to get some curve. You'll have to forgive the absence of the y-axis. I don't know where it's gone. Alright, now, so this is... yeah, we'll also have to forgive the phase shift. Alright, now we have our points. Okay. Mm-hmm. That was a little bit more artistic over there. Yeah, let me see. Well, and notably nothing about this function changes the up-down offset. Am I correct about that? Actually, no, you're not correct about that. Interesting. Why would I not be correct about that? Well, let's do a little bit of side thinking here. Okay, so if I have 6 times the cosine squared, let's see, 6 times the cosine squared of, no, right, well, okay, 6 times the cosine squared of x minus 3 is equal to f of x, and then I simply say cosine of x minus 3 equals f of x. Okay, and then I do 6 times the cosine of x. Yeah, we could do that though. I wonder. It's like f1, f2, f3. We could do various combinations like just 6 cosine of x is equal to f4 of x. Yeah, there's the squaring. What does that do? This one might prove to be critical. What do I mean? Well, let's look at simply the cosine squared of x equals f5 of x. Alright, f5 of x is equal to the cosine squared of x. Right, if I say that a is equal to the set containing as elements pi sixth, pi fourth, dot dot dot, 7, no, it'd be 11 pi sixth. B is equal to 1/2. No, hold on. Root 2 over 2, right? No, hold on. Root 3 over 2. Yes. Root 3 divided by 2. Root 2 divided by 2. 1/2. 0. 1/2. Oh, that's not correct. No, that would be cosine. And then for that matter, so this would be, yeah, okay. Let's reorganize on the next page. Alright, so we're gonna say A is equal to the set containing its elements, pi divided by 6, pi divided by 4, pi divided by 2 pi divided by 6. The pi divided by 6 convention is a pretty solid one. 2 pi divided by 6. Dot dot dot. Alright, so if I have B, okay, let's say we'll just call this a sketch, an outline. We'll say what we're looking for here is, let's do f sub 1 is equal to fx is equal to cosine of x minus 3. Then how about, for good measure, f of x is equal to cosine of x minus pi divided by 4 pi divided by 6th. I don't think having the clip does this any good. Yeah. f2 of x cosine of x minus pi 6th. Okay. f3 of x is equal to 2 times the cosine of x. Okay, f4 of x is equal to the cosine squared of x. Alright. B is equal, B1 is equal to the set containing yes, well, in retrospect, we should have had f5 of x is equal to the cosine of x, because that will just give us a handy table from which we can copy values. Alright, so we're going to say b sub 5 is equal to the set containing as elements pi 6. Actually, we can copy most of these values, so that'll be root 3 divided by 2. Yeah, we'll go ahead and do that with, I guess we'll do parents. Okay. I have to order collection of parents, please. I'm gonna cut out the commas. 1/2, that would be incorrect. This would be -1/2. Yeah, alright, I will finally use commas. Alright, negative 1/2, negative root 2 over 2. And then negative 1. Ah, yes, we should have had 0 in there probably. Oh well. Alright. Well, yeah, actually, we'll get that for free. Okay, now we need merely, for b sub 4, we need merely square all of these values. So this will be 3 divided by 2. Oh, we're not gonna, I mean, we can fit it. Oh, and also we need to put the 0 element in front. Yeah. Alright, we'll do... This actually just be 1, rather. Alright, 1 phi of 0. Ah, yeah. Indeed. Alright. So we have 3 halves, 2 halves. Indeed not. We have 3/4, 2/4. We have 1/4. We have 0. We have 1/4. We have 2/4. Yeah, I'll just keep this position. 2/4. Dun, dun, dun. Yeah, well, we can't fix that one, is the thing. We could rewrite this page. Yeah, well, I mean, the... part of the point here is that if we put in the effort to fix what we call a mistake, or what we call mistakes, the next time those mistakes become choices, available choices, we might not make them. Which in this context means that I want my one-shot execution of a page of math notes. I want my one-shot execution of a page of math to be high quality. I want to be able to make choices that fall on the better side rather than the worse side. Okay, and now how am I going to do that? I am going to rewrite this page patiently. Okay. Now, if we could restructure these. I'm thinking we can lay out these across the page, but I think we would take up more than a line. If we had one more, we could split it up into thirds. For now, I think f1 of x will be equal to the cosine of x. Okay. 2 of x will be equal to, what do we want to highlight? The distinction between the unsquared and the squared form is a candidate. We could do 2 cosine x to highlight that there is not a difference. I like that idea. Okay. Now we're going to have the cosine squared of x. What is that going to contrast with? We could put that alone in the center, maybe. That's the biggest change, I'd say. Cosine squared of x. Oh, we messed up. But just keep it. Alright, f3 of x. And now f4 of x is equal to cosine of x minus 3. And f5 of x is equal to the cosine of x minus pi sixth. Say we're reserving red for the original function, go straight to orange. Spanish orange. Green. Alright, now what? Now we're going to have B1, which is equal to the set containing its elements. Ah, yes, okay. A is equal to the set containing its elements. 0 pi divided by, oh, so, yeah, but the answer field down here works fine. Pi divided by 6, pi divided by 4, 2 pi divided by 6, dot, dot, dot. Okay, now we're going to have 1. So why would I put a space here? Solely because of this one. Interestingly. It's only because of this one that I need a space here, because when I run cosine of 0, I'm going to be running cosine of negative pi sixth, which will instead be root 3 over 2, which will need this extra space. Now what? 0 pi. Let's see, root 3 over 2. And then root 2 over 2. 0. 1/2. Now here, similarly, we need to keep a space. And now set containing elements 2, root 3, root 2, 1, 0, negative 1, negative root 2, negative root 3. Okay. B3. That would be 1. And then it would be 3 divided by 4. And then 2 divided by 4. And then 1 divided by 4. 0. 1 divided by 4. 2 divided by 4. And 3 divided by 4. Okay, B4. Cosine of x minus 3, that would be negative 2. Okay. Interesting. Okay, and then B5. Alright, so now we're going to have root 3 divided by 2. Hmm. Turns out we needed the coloring scheme. Well, you look at that. The coloring scheme came in handy. Would have come in handy anyway. like there's too much shame in mathematics. There's a door in front of you. Okay? It won't open until you solve a math problem. You have an indefinite amount of time in which to solve it. Do you have a practice? Because if not, you're going to have to come up with one on the spot. And it might not work well. Wait a minute. Something went wrong. What went wrong? Well, that's an incorrect value, but I don't think that's what went wrong. Let's see here. there's just that one value. Okay. Now what does all of this tell me? Multiplying the entire function by 2 merely doubles every value. Okay. Squaring makes every value positive, as we knew to look for. Interestingly, it also removes all of the root values. We have only rational values after a squaring. Then minus 3 is going to make these values, it's going to be a direct y reduction in values by 3. Okay. And subtracting pi divided by 6, which doesn't happen in this function, cranks the clock back. Okay. And what do I want to do with this observation? Oh, pi divided by 2. Actually, there is some. It doesn't exactly crank the clock back because if. No, wait, that's not what we're on. Hold on. We're on. Alright, we're looking at 6 cosine x minus 3 equals f of x. Okay, and we're merely observing that multiplying by 2. Yes, but so these factors come together, right? What we wanted to do here was sort of a process of logical elimination, where we say, well, 2 times the cosine of x only increases the peaks and the troughs, the magnitude of the peaks and the troughs. Okay, and then squaring makes all the values positive. So it's like we wanted to accrue properties and then use logic on the properties. Okay, now the multiplier by 6 and the squaring. Well, multiplier by 6 once again increases the amplitude. Squaring makes all the values positive, but subtracting by 3 is going to produce negative values. Because notably, even in the case where we have actually, it's interesting, we get the 0 alignment. We get 0 at the cosine of x, and we also get 0, that would be over here, the coloring scheme. Actually, yeah, we can do something about that. Okay, now, so we have the squaring, and we have a 0 value, and we have 2 times the cosine of x, we also have a 0 value. So this function is going to be I think that's a valid line of reasoning. This function is going to be 0 for these two 0 values. Or rather, this function is 0 here, and consequently, well, no, rather, even both 2 times the cosine of x and the cosine squared of x are 0 for this input value, and consequently 2 times the cosine squared of x would also be 0. How do I know that, though? Well, it doesn't seem like the best line of reasoning either. You'd want to say the squared function is 0, and then if you multiply 0 by 2, you get 0. As opposed to saying, for instance, that It's the coincidence of 0 evaluations that gives me the 0. Though if we could reason like that, that would be interesting. Maybe we can, I don't know. No, but what are we taking away from this? We have zeros for 6 cosine squared of x, and those zeros will drop below into negatives due to the -3 application. Now, a question would be, does this make all of the values negative, this -3? No, it does not make all of the values negative because the amplitude will be 6. Most obviously. Wait a minute. Yep, here. No, amplitude won't be 6. It will be. There we go. 2. Yes, so the amplitude will be 6. This is the greatest value. Alright, and then the amplitude will be 6, which means that when we reduce the y value by 3 by a constant amount, not the entire function will be negative. Okay. Alright. Well, I thought that was pretty interesting. I think we could. Is that a good usage of an hour? Probably. I mean, this is practice for working through concrete mathematics. I mean, I'm not saying we're going to work through concrete mathematics. I'm rather making the observation that this is in the same skill tree, as it were. We're leveling up some relevant skills like notebook management and coloring. Yes, coloring, a critical skill. In this case, well, yeah, we probably could have reserved coloring for only the first and the last of these, because it's only this that where we gain something by. Well, it's only here that we change the coloring to match the idea. I spent the axiomatic set theory time slot thinking about talking through the prospect with our interlocutor, talking through the prospect of an overlap dialect and sort of subset of both lean and racket that is transliterable, transpilable, you might say. Yeah, if you just want to talk about throwing things in a pile, sure. Transpilerable. So the project idea that emerged is that so when we're solving LeetCode problems in the upcoming weeks, we're going to try to stick to a limited subset of racket and see if we can solve problems using that limited subset. Okay, and that limited subset is readily translatable with minimal loss. Like a macro scheme on either end would be good enough for literally translating. And then the side point here would be that, well, yeah, I mean, with these samples of literal translation, we could just write the lean code directly with enough practice. Write the lean ward. lean ward code directly. And the idea here is that so long as we stick to this translatable subset, we'll be able to rewrite our racket code in lean and prove various characteristics about it. So that's what I spent my time thinking about. That and how to occupy mealtime stretches. Anyway, I'll be back. Usually, most of the time. We'll see what we do tomorrow.